802.11 standards. Think of the 802.11 standards as the rulebook for the invisible conversations happening all around us, every single second of every single day. These standards are maintained by the IEEE, the Institute of Electrical and Electronics Engineers, and they define exactly how data is encoded into radio waves to move between your devices and the internet. Over the last 25 years, these rules have evolved from a slow, shaky whisper to a high-speed, rock-solid shout. Understanding this evolution is not just about memorizing letters. It is about understanding how we solved the massive technical challenges of interference, distance, and crowded airwaves. The humble beginnings, 802.11 legacy and 802.11b. The story starts in 1997 with the original 802.11 legacy standard. It was slow, reaching speeds of only 2 megabits per second in the 2.4 gigahertz band. To put that in perspective, it would take you several minutes just to download a single high-quality photograph today. It used a technology called frequency hopping spread spectrum, which was revolutionary for the time but very limited in capacity. However, the real breakthrough happened in 1999 with 802.11b. This is the standard that brought Wi-Fi into our homes and offices. It increased speeds to 11 megabits per second by using a technique called direct sequence spread spectrum. Even though it was faster, it still lived entirely in the crowded 2.4 gigahertz band, meaning it was constantly fighting with microwave ovens and cordless phones for airtime. The split, 802.11a and 802.11g. Right as 802.11b was becoming popular, the engineers realized we needed more space. This led to 802.11a. This was a radical departure because it moved into the 5 gigahertz band, which was almost completely empty at the time. It also introduced OFDM, or orthogonal frequency division multiplexing. This is a complex way of breaking a single data stream into many smaller, parallel streams that travel simultaneously. This allowed speeds to jump to 54 megabits per second. The problem was that 802.11a was not backwards compatible with the millions of 802.11b devices already in people's hands. To fix this, we got 802.11g in 2003. It took the high-speed OFDM technology from the standard and brought it back down to the 2.4 gigahertz band. This gave users the best of both worlds, 54 megabit speeds and compatibility with their older gear. For a long time, G was the king of the wireless world, but as we started watching videos and sharing larger files, even 54 megabits started to feel like a bottleneck. The MIMO revolution, 802.11n Wi-Fi 4. In 2009, everything changed with the arrival of 802.11, and this standard introduced two massive technical leaps: channel bonding and MIMO. Before 802.11n, every router used a single antenna to talk to a single antenna on your laptop. This is like trying to move a mountain of dirt with a single shovel. MIMO, which stands for multiple input, multiple output, allowed the router to use multiple antennas simultaneously. It could split the data into different paths, bounce them off walls and ceilings, and recombine them at the destination. This made the connection incredibly stable and much faster. Combined with channel bonding, where we doubled the width of the radio lane from 20 to 40 megahertz, 802.11n pushed speeds up to 600 megabits per second. This was also the first dual-band standard, meaning it could run on both 2.4 and 5 gigahertz at the same time. This is where the Wi-Fi Alliance decided to start using simpler names, calling this generation Wi-Fi 4. Gigabit everywhere, 802.11ac Wi-Fi 5. By 2013, we were no longer just browsing text websites. We were streaming high-definition Netflix and using cloud storage. We needed even more power, which led to 8-0-2.11ac, or Wi-Fi 5. This standard focused almost entirely on the 5 GHz band. It took everything 802.11n did and turned it up to 10. It allowed for even wider channels, up to 80 or even 160 MHz. It also introduced beamforming. Instead of the router shouting the signal in all directions like a light bulb, it could now focus the radio energy into a specific beam directed right at your device, like a flashlight. This significantly increased range and speed at the edges of the room. The most important feature of Wi-Fi 5 was MU-MIMO, or multi-user MIMO in older standards. The router could only talk to one device at a time. It would talk to your phone, then your laptop, then your TV, switching between them so fast you didn't notice. But with MU-MIMO, the router could actually hold conversations with 4 different devices at the exact same millisecond. This was a game changer for crowded households with dozens of connected gadgets. Efficiency over raw speed, 802.11 Wi-Fi 6 and 6E. In 2019, the engineers realized that just making the pipes wider wasn't enough. In a busy coffee shop or a stadium, the sheer number of devices trying to talk at once was causing the network to collapse. This led to 802.11ax, known as Wi-Fi 6. Wi-Fi 6 is all about efficiency. It introduced a technology called OFDMA, which is a highly advanced way of sharing a single channel. Imagine a delivery truck that used to only carry one package at a time. With OFDMA, that truck can now carry dozens of small packages for different people in a single trip. This reduced latency or lag, making the internet feel much more snappy even when the network was crowded. Then came Wi-Fi 6E. The E stands for extended. This is the exact same technology as Wi-Fi 6, but it unlocked a brand new, massive highway in the 6 GHz band. This was the first time in 20 years that we were given new airwaves to use, and it provided a greenfield environment with zero interference from old legacy devices. The future, 802.11b, Wi-Fi 7. We are now entering the era of 802.11b, or Wi-Fi 7. This is being called the extremely high throughput standard. It is designed for things we haven't even fully realized yet, like ultra-high definition virtual reality and wireless 48K video. Wi-Fi 7 introduces multi-link operation, or MLO right now. Your phone chooses one band, either 5 or 6 GHz, and stays there. With MLO, your device can actually use both bands at the exact same time. It's like having 2 separate internet connections bonded together into one massive, ultra-fast pipe. It also uses 4K QAM, which is a way of packing 20% more data into every single radio pulse compared to Wi-Fi 6. The result is theoretical speeds of over 40 gigabits per second, which is faster than most physical office cables. The golden rules of compatibility. As you move through your career in cybersecurity and IT, you must remember one final rule: the slowest device determines the speed of the conversation. Even if you have a brand new Wi-Fi 7 router, if you connect an old 802.11g printer to it, the router has to use an older, slower preamble to make sure the printer can understand what's happening. This creates overhead that can slow down every other device on the network. This is why, as a security professional, you will often recommend retiring very old legacy devices or placing them on their own isolated VLAN to keep the rest of the high-speed network performing at its best. By mastering the history of these letters and numbers, you can look at any piece of hardware and instantly know its strengths, its weaknesses, and exactly how it is going to behave on your network.